Thank you very much for that introduction, Daniel. My name's David Bruhwiler. I'm talking about effective software collaboration between industry and academia and national laboratories. And it's a pleasure to be presenting to the OWLE Colloquium. Here's a relatively detailed introduction. I'll be bringing this back periodically to remind you where we are in the flow. I'm going to start off with some background and context. So I'd like to emphasize that many of the ideas I'm presenting here today are emerging from the snowmass community, in particular from the applications and industry topical group of the community engagement frontier. So snowmass is a US high energy physics activity, but and it has a significant particle accelerator component, and it has a significant international component as well. And so part of what's done for snowmass is the creation of letters of interest, or LOI. And I led an LOI, which you see referenced here with all of the co-authors. And there's a link which tells you where you can download it. The LOI received relatively wide-ranging support from industry. The other company besides RadiaSoft was Kitware, which is a US open source company, which writes a lot of software that's used by the scientific community. Universities are NIU, that's Northern Illinois University, the University of Strathclyde in Scotland, and Korea University. And of the US national laboratories that co-signed, we have Fermilab, Argonne National Lab, and SLAC National Accelerator Lab. However, this presentation does reflect my personal opinions, which is why I didn't put all these people's names on the list of co-authors, although they did contribute to some of the ideas that I'm presenting. The technical software specific ideas are written down in some detail in the IPAC 19 proceedings, which you can see referenced here with a link showing where you can find it. Okay, so I'll give you a brief history of my participation in industrial R&D, so you can better understand where my point of view is coming from. So down here in the lower right, you can see in 1992, I began working with Grumman Aerospace Corporation. That was just about a year after I finished my PhD. Grumman was bought by Northrop, which became Northrop Grumman. And so I continued in that organization for approximately 6 years. After that, I left the aerospace industry and I moved back to Boulder, Colorado, which is where I did my PhD work, and that's where RadiaSoft is located. And I joined TechX Corporation, and I began participating in the SBIR program. That's a US funding program for small businesses, which I'll talk about more in a couple of slides. And I was at TechX for 14 years, after which I left to co-found a startup called Normforge in 2012. And that was an open source company designed to support technical standards committees with web-based, cloud-based collaboration software. And it was a good idea, but our customer slash evangelist supporter lost interest, and ultimately that company did not succeed. So after Normforge folded, I co-founded RadiaSoft in August of 2013, where I serve as president and CEO. So the Normforge and RadiaSoft were built on open source business models. All of these companies, with the exception of Normforge, involved significant collaboration with academia and with industry to further industrial R&D objectives. So, okay, so I'm going to give you a brief overview here of Serapo. which is an open framework for cloud computing. And this is the flagship software product at RadiaSoft. And I'm going to be talking about it more later. So this is just a brief orientation. So here you see a screenshot of the main Serapo page on GitHub. Go to github.com/radiasoft/Serapo. From the very first few lines of code, beginning approximately 7 years ago, all of the Serapo development history is here. And all of the bug reports and some conversations between the developers. And so it's been not just open source, but it's being developed in an open way. Serapo is also a free scientific gateway. If you go to https://serapo.com, you will find that you can click on the supported codes link in the upper right, and you will find 13 or 14 codes there, mostly related to particle accelerator technology. We have a small software team with just 4 people, and it's impressive to me that we're able to support 14 codes. And the way we do that is, one, there's a shared JavaScript user interface, and we are leveraging a lot of open source JavaScript libraries which solve the cross-platform problem of multiple browsers on multiple operating systems. On the server side, we solve the cross-platform problem by eliminating it. We use application containerization technology with an open source software called Docker. And so we are supporting all of these codes on one flavor of Linux. And so we are not devoting time and money and people power to the problem of cross-platform compilation and testing. That's essential for the success here. So the power of Serapo for users is that there's ease of use. You can model magnets, you can model X-ray beamlines, you can track particles through accelerators in your browser. There's nothing to install. It's intuitive to use. You get instantaneous collaboration. If you're working on a Serapo simulation in your browser, you just copy the URL out of your browser and you can send that in an email or an instant message to a collaborator. They paste that into their browser wherever they are in the world. Then they are offered by the Serapo server to create a copy of the simulation. You click yes, and in less than a minute, you're up and running with exactly the same simulation as your collaborator. And now you can talk about what you're seeing in real time, and there's no long conversations about, oh, I forgot to send you this input file, or you're using the wrong version of the code, or all these types of things. You can archive and save your simulations, and you can resume work a year later with 0 startup time. And importantly, the GUI is not a trap. At any point, if the GUI is limiting what you're trying to accomplish, you can export all your files and move to command line execution on any system where the relevant physics code is installed, of course. And this also, you can also import these files into the GUI. And so this is a great way for a GUI user and a command line user to collaborate together, each working in the way that they are most effective. All right, so the SBIR STTR program was begun in the US in 1982. It was a congressionally mandated program that all of the federal funding agencies in the US have to direct a couple of % of their non-construction R&D towards these awards that would go to small businesses. And the intent was to stimulate technological innovation, to have small businesses contribute in ways that other parts of the federal government might not contribute, and therefore help to meet federal research and R&D needs. And also to encourage participation of disadvantaged small businesses and those that were more than 50% owned by women. In more recent years, the intent has expanded a little bit, where there's more emphasis on the commercial potential of what's being funded. So even Silicon Valley venture capitalists have said good things about the SBIR program, because this is a way of fostering deep technology business development, which can take decades sometimes, and it results in occasionally in very successful businesses that have technologies that would not have been developed in a VC environment. Okay, so I'm now going to give you some caveats. I'm going to state the problem, and I'm going to specify the goals of what we're trying to do here. So some caveats and some definition of scope here. So the scope of collaboration is obviously very broad, and so we need to narrow it down a little. I'm considering only software here. There's some parallels with collaborating with hardware, but in many respects it's quite different. My experience is in the US. And so I have a very US centric point of view, and I'm not talking about other countries here, but I would be happy in the discussion to hear about what's going on in other countries. And then my experience is primarily with the particle accelerator community, and I'm sure this landscape is different as you go to different scientific communities. Okay. Secondly, my perspective is from an open source software company. And the ideas that are being presented here were really motivating RadiaSoft's open source business model. And I will note that there is another great US open source company, Kitware, which is collaborating extensively with DOE labs and universities and working quite a bit in Europe as well. They are, a lot of us are using their software. RadiaSoft uses their software a lot. And then it's worth noting that various other companies in our community do develop closed source software. And I'm not here to engage in a battle between open source and closed source. Commercial software is of course a valid business model, but I'm passionate about open source. So the academic community is an essential part of the bigger picture, and I did add academia into my title from when I previously gave this talk. With pretty much everything I say about, much of what I say about the labs applies to universities as well in many regards. So in any case, I'm hopeful that this presentation is transcending some of these caveats. I've tried to incorporate many ideas from the particle accelerator community, and I think there are a couple of ideas here that are potentially of general interest, but of course, just wanted to be clear about the scope of the presentation. So here's just two examples of successful collaborations, just so we can have some concrete success stories in mind. So RadiaSoft began working with NSLS2 at Brookhaven right after we were founded. One of our first proposals that got funded was a collaboration with Oleg Chubar at the NSLS2. And this was a project to support development of the SRW code that stands for Synchrotron Radiation Workshop. This is probably the premier physical optics code, certainly in the X-ray community. It's can calculate synchrotron radiation and propagate wave fronts, interacting with a variety of sophisticated optics that are used in X-ray beamlines. There was a phase 1 SBIR award, which went to phase 2, and DOE, or the SBIR program generally, added a 2A possibility recently, where basically your 2-year phase 2 award can be extended for another 2 years. And that happened in this case. So there were 5 years of support. And then after the 5 years, there was a 3-year contract to support Serapo servers on site at BNL. And that 3-year contract is wrapping up. So we're at close to the 8-year mark of this collaboration. and the company's 8 years old. So, and we are, negotiating an extension of that support contract. So this is an example where the SBIR program developed a technology, and in fact, this was the project that originated Serapo. And it was of sufficient value to Brookhaven, in particular the Serapo app, that they're continuing to support us outside of the SBIR program. Another example of a collaboration is with the US Particle Accelerator School, USPAS, and that's a multi-institution organization. However, financially and contractually, they are closely affiliated with Fermilab. And RadiaSoft provided free support to the US Particle Accelerator School for a number of years. We provided volunteer teachers. We paid for scholarships for students. And as Serapo became useful, we provided Serapo for free, including access to the servers. And then about a year ago, decision was made that we should formalize this, and USPAS and Fermilab have contracted with RadiaSoft for annual Serapo support. And we've done that for the last 2 sessions, and it went very well. So, okay, so halfway through the talk here, let's state what the problem is. So contracting with the national labs is very fruitful. We presently have contracts in place with Fermilab, Brookhaven, Argonne, and Oak Ridge. Actually, the contracts come and go. Like, I think our active contract with Fermilab, I think, ended about a month ago. But in any case, and there's other labs that we've been working with. We almost always we generally have a contract in place with Berkeley. At this moment, I'm not sure that we do. We've contracted with Los Alamos and Livermore. And it's always professionally rewarding, and there's always an effective transfer of technology, that is one of the main points of the SBIR program. However, it is challenging to negotiate and manage these contracts. Each contracting office at each lab has different procedures and policies, and generally these offices are inflexible regarding contract language. I mean, we're going through this with Brookhaven right now. We're negotiating 3 contracts simultaneously for 3 different projects. And it's not unusual that there will be a 2-month wait. And I understand why this happens. We are a very small part of what's going on in these contracting offices, right? They're dealing with $100 million contracts. And then here we are, this SBIR company that's trying to negotiate $100,000 contract in one direction or the other, and we may have to wait 2 months before a contract is drafted. And then at that point, we're into a 9 or 12-month project, and there's really no time to negotiate because the principal investigator at RadiaSoft and the folks at the lab, the technical people, are just like, we've got to start moving. We need this contract in place. And so then the small business owner has to simply sign the contract. There's no time to negotiate. And even, you'll even get say, here's a draft. And if you want any changes, there's going to be more delays. It's almost like, it's not very friendly. And so that's one sort of piece of the difficulty. The other piece, which is not anybody's fault, and it's harder to solve, is that these collaborations are typically ad hoc, and they're often short-lived. So, I mean, everybody knows this, and this is the world you live in. But in order to really have a long-term and a deep collaboration between 2 institutions, you've got to kind of keep working at getting the next thing funded, get a new contract, execute that, and then when it's over, and there's, and therefore it's difficult for the small business to really fully understand the needs of the lab or the university. Situation with the universities is quite similar in many cases. And also the laboratory personnel don't appreciate the full capabilities of the business because there's just your interaction is defined sometimes rather narrowly by these contractual relationships. Of course, you get to know people over the length of a career, that helps, but you know, that's 10 years, 20 years. So what are we, you know, so my intent is not to complain. I know that people at the laboratories are following the rules and they're incentivized in certain ways and they're doing the best they can, just as the small businesses are doing the best that they can. And so it's, the intent is not to complain, but simply to identify some of these difficulties and suggest how maybe there might be some ways to do better in the future. And these are not like quick fixes. Again, this came out of the SNOMAS. The idea of this presentation and actually trying to talk about these things in a public forum came out of the SNOMAS exercise that's ongoing in the US high energy physics community. And there the outlook is 10, 20, 30 years. So that's sort of, we're trying to think about how could we do better over long time scales. So goal number 1, to achieve better science and engineering with greater efficiency is, you know, each institution should concentrate on their core competencies. And so, for example, from a software point of view, one would expect labs to take the lead and universities to take the lead on development and implementation of particle accelerator design codes with unique capabilities that are essential for the design and operations of that institution. However, ease of use, for example, GUI development may not be a core competency, and software sustainability may not be a core competency. For example, I don't know if I sufficiently emphasized it, but when I pointed out that, you know, we have 4 software developers and we're supporting 14 codes, and we don't ask for anything from the software development teams at the labs and the universities. We wrap the GUI around the code, and as the code changes, we adapt. So we do not impose any burden on the code developers. And so how can we sustain, you know, 14 different codes with 4 software developers? And the way that's possible is with making effective use of software containerization and sharing.
Do we want to watch these?
Excuse me, someone needs to mute their microphone. And also taking advantage of open source JavaScript libraries, which help to manage the cross-platform headaches associated with different browsers on different operating systems, and then, you know, sharing that code across the GUIs for many different apps. There would be no way to develop a completely unique GUI for each code in a, you know, in a sustainable way. Okay, so now labs will purchase or use for free relevant software from other institutions. And the question really is, what is or is not a core competency? And of course, this is every organization goes through this. Every organization wants to be self-sufficient. But if management is erring on the side of self-sufficiency, you know, why are they doing that? Sometimes they're doing it because outsourcing is difficult. So one of the points here is that core competencies should be more precisely defined, and outsourcing should not be difficult at the labs. So more efficient technology transfer to the private sector is another goal. And as I noted previously, the SBIR program is very effective in many ways. However, activities outside of the program could add a lot of value. And then goal number 3 is to hopefully and potentially improve the career pipeline for our entire community. And I think labs, companies, and universities all want our scientists and engineers to stay in the field. I mean, this is actually a big topic in the snowmass frontiers that are reconvening now after the pandemic slowdown. And, everybody is aware of this problem. And also, early and mid-career professionals want flexibility. So I would suggest that more flexible movement of personnel between different types of employers could potentially help both problems. All right, so I'll give you a couple of specific ideas for new approaches and the associated benefits. So idea number one, try to integrate industry scientists and engineers in laboratory activities. Labs now, a good thing that's happening is labs are constantly fostering community-wide coordination of long-term R&D efforts through dedicated workshops and reports. And this engages many members of the, decision makers from Washington, university, scientists, and industry. And roadmaps get created for technology readiness in areas of critical need. And industry does play a role in providing feedback or even helping to contribute to the development of such reports. The recommendation is to find comparable mechanisms to identify long-standing partnership opportunities between labs and businesses in support of the long-term community aims. So such long-term partnerships would enable businesses to sustain expertise and personnel. And then the product development teams at such businesses could cross the proverbial valley of death in technologically adjacent commercial markets. So the point here is that if businesses can make substantive contributions to the activity of the laboratories, and if those businesses over time can become self-sustaining through commercial activities, which are technologically adjacent to what's being done with the labs, then that could be mutually beneficial. But if everything is focused on short-term contracts, or a new facility is about to be built and we need contribution from industry, and then once the facility is built, industry is not needed so much, and so all of a sudden there's no work for those companies, it becomes quite challenging for the businesses. So, okay, idea number two. So find more flexible ways for laboratory scientists and engineers to work on company projects. So first, a few remarks. One is that the U.S. Particle Accelerator School is a really important resource, and it serves as a great bridge between academia, industry, and the national laboratories, while simultaneously solving an important problem for the particle accelerator community, which is that I think it's perceived that we have a need for more scientists and engineers in our field, and we've got to cultivate the students and early to mid-career scientists and engineers who might be interested. Another interesting program is called the I-Core program. And RadiaSoft personnel, including me, participated in the NIH version of this program. Now, until recently, the Department of Energy I-Core program was only available to laboratory scientists. The idea was help a scientist in the laboratory take a technology outside of the lab and commercialize it. And recently, just within the last year, DOE has brought I-Core to the SBIR STTR program, and I think that's great, and that's going to be helpful. But my recommendation here is that formal mechanisms should be developed to support extended visit of laboratory personnel on site at U.S. companies. Now, this is something, of course, that could be funded directly by DOE, but that's not the only possibility. And of course, asking DOE to create a new category of activities to be funded, of course, is challenging, because then that money has to be taken from somewhere else. One idea is that the visits could be paid for by laboratory tech transfer funds. All of the labs have significant tech transfer budgets. Or also the SBIR rules could be modified to allow for special contracts of this type. This is obviously not something that's going to happen quickly. These rules don't get changed very easily, but I feel it's worth suggesting. So I was recently told that the US accelerator labs have some programs supporting extended industry visits, and I haven't yet taken the time to find out more details about that, but I do intend to do that. Okay, so we're getting close to the end here. So I'm going to get back to the Serapo framework and how it's a useful example for facilitating collaboration. The problem that it was developed to solve. Then I'll discuss a few benefits of open source software. And then, because it's somewhat relevant, discuss what are the required characteristics of a computing framework, because this is an idea that's being discussed a lot in the community. And I think it's an example where industry could make a positive contribution. Okay, so what is the problem that Serapo was developed to solve? So there are many free world-class particle accelerator codes in the DOE labs and at universities, and not just in the US, obviously, but all around the world. However, users have to learn complicated, error-prone command line workflows. You've got multiple input and configuration files, then you're going to execute it on an HPC cluster, so you have to learn all the rules and workflows of that HPC environment. And then once you've run the software, you have to learn the post-processing tools and the visualization tools. And so, of course, there's a wide variety. Some codes are easier to use than others, but generally speaking, a student or a postdoc comes in and they start working with the code. And after a year or two, they are an expert in that code. And so you go around the world, you have several people who are experts in a few different codes. And so why doesn't more effort go into ease of use? Well, developing a unique GUI for each code is not really practical, and in any case, funding is not available. Is there significant reuse of the codes? Are the codes being benchmarked? And can you couple the codes together to solve more and more complex problems? The answer to these questions, of course, is yes, although not enough. And developers and scientists are motivated to work on these things, but they're not necessarily incentivized. There's one example in the US, the CAMPA project, and I have their URL here, is working on these issues. And then there's the question of long-term sustainability for each code. Basically, many of these codes have development teams that are dominated by 1 or 2 people. And that's great for 10 or 15 or 20 years, but eventually the question arises, how is this code going to continue to thrive after that person retires? And sometimes, there is a sustainability question is addressed, but often these efforts are ad hoc and they're expensive, and sometimes they really aren't addressed. So, question: can I see this solution? Yes. You can go to www.serapo.com and click the supported codes menu, and you can start using the codes. If you've never used Serapo, you will be asked to go through an email-based registration procedure. But all right, so let me digress a little bit and talk about just a few of the benefits of open source software. So one example you can of a rather detailed document is you can look at the cyber infrastructure framework for the 21st century, a vision and strategy for software for science, engineering, and education. This is an NSF document from 2012, and it talks a lot about open source and open science and the reasons why these are important. One benefit is that the algorithms can be inspected by all. Ultimately, looking at the source code is the most detailed and accurate representation of what's actually happening in the software. And so this openness of the source code is important for correctness and reproducibility and benchmarking, and therefore important for doing science. At RadiaSoft, and I think this may be true at other institutions, it's really necessary to recruit and retain world-class software developers. Developers like their work to be visible, and most Google developers, for example, are not working on open source projects. There are, of course, many open source projects that Google is involved in, but you know, we can't compete with Google on salary or benefits or prestige or really anything else. So we provide an open environment where software developers and scientists are working together, and there's no social hierarchy. And you know, that's the only way we can find here and there like really great software developers that are interested to stay at RadiaSoft rather than going to Google and making a lot more money. Open source software facilitates collaboration. So it removes a lot of barriers related to money, contracts, IP agreements, licensing, et cetera. When I was in a more of a closed source environment, software would be developed that was never used because of these barriers. Or you're gonna have a collaborative relationship, and the first thing that hits you in the face is you've got to start signing NDAs and IP agreements and paying licensing fees and all these other things. And it's just tedious and not very productive. Now, I know if people have IP in their software that they want to protect, there's no way around that. But an open source point of view is that there's science in the software, there's a lot of value in the software, but that should be shared, and there's other ways to make money, not from trying to charge people for the software. And the other way it facilitates collaboration is it builds trust, and it significantly reduces concerns about longevity and control. If RadiaSoft goes out of business, the Serapo, people had access to the Serapo repository, and maybe, Serapo could live on in the event that something bad happens to RadiaSoft. That's true for any large software collaboration in any institution. An institution can lose interest, the developers can lose interest, but the software has a chance to live on. This slide is adapted from a presentation I made together with Jean-Luc Vey from Lawrence Berkeley Lab, meeting beam physics grand challenges via HPC. And so there is this idea of developing various types of software frameworks that are going to enable multi-code interaction, so multi-physics, enable reproducible computing, enable benchmarking, enable the integration of a hierarchy of simulation models from very fast and approximate to slower and higher fidelity, and integrate these with control systems and with other systems. And so some of the characteristics that should be required are listed here. And so in my opinion and Jean-Luc's opinion, open source that's developed publicly on GitHub or Bitbucket or GitLab, this is very important. You need to support many codes with no requirements imposed on the code developers. You need to provide ease of use for students and other non-experts. You need to support relevant facilities and particle accelerator technologies. Reproducible computing is a problem that's not been adequately addressed by our community or other scientific communities. You want to be able to come back 10 years later and rerun the simulation and get the same answer. And you want to be able to work on a variety of hardware platforms without locking users into a particular technology. Okay, so I'll go to my conclusions and then I'll stop. All right, so I think working to improve lab industry collaboration is a worthy goal. Some long-term ideas were suggested, and some important software-specific issues were, I hope, clarified. One is that open source software brings many advantages. There are many other requirements for a multi-institution software framework other than just open source, and I think industry can make a strongly positive contribution to such an effort. And then I talked a fair amount about Serapo, which is the flagship software product at RadiaSoft, which of course I think is very important and useful software. So I will stop there and take questions. Thanks.